Welcome to section 5.2, addition, rule, and complements. So we're going to look at the probability of two events now, two events. So for instance, we can ask what's the probability of rolling a die, 6 sides to a die, and then getting a 2, 3, or 5. All right, so we have 3 events in that case, 2, 3, or 5. So to help us figure out this rule, we're going to look at Venn diagrams to help us develop all our theory. And in 5.2, we're going to, or for right now, we're going to consider events that are disjoint or mutually exclusive. So we're going to define what that means. Disjoint or mutually exclusive means the events have no outcomes in common. So another name for disjoint event is mutually exclusive. So let's draw a picture. So a Venn diagram, we're going to have a rectangle for our Venn diagram, and it's going to represent the sample space. So we'll have an S for sample space. And now events can be represented by circles. So we're going to be rolling our die here. So let's suppose that this circle represents an event, we'll call it E. And let's say that means we get a 2, a 3, or a 5, like from above. And then let's define another event. We'll call it event F. So we'll have another circle. And event F means that we roll a 1. Okay, so let's write down these things. So far we have our sample space, which lists out S for sample space, which lists out all possible outcomes from rolling a die. So we can get a 1, 2, 3, 4, 5, or 6. Just one die, not 2 dice. Event E was getting a 2, 3, or 5. And then event F was getting a 1, rolling a 1. Okay, and then we also like to label what's not in an event, what's left over in the sample space. So let's see, we have 1, 2, 3, 4 is not in an event, but it's still in the sample space, so we'd want to represent it. And then 5, 6. 6 is not in an event, but it's still in the sample space, so we'll just write it outside the events. So now we're going to figure out the probability of the probability of E or F happening. So we're going to be looking at the probability of 2 events. So what's the probability that we roll a die and we get a 2, 3, 5, event E, or we roll a die and we also could get a 1. So if we just visually look, let's count up the events in E and F, 1, 2, 3, 4, and out of how many outcomes possible? Well, the probability that we are going to land in E or F is 4 outcomes out of 6 total outcomes. Okay, and then how did we do that? So let's write a little bit down here. It was a counting game, right? When we count things up, we use the number n. So we counted up the things in E or F. Could be in one or the other. And then how we did that is we counted them up individually. So again, little n means the number of outcomes in event E or number of outcomes in event F. And once we had those numbers, to find the probability, we took them out of the total outcomes in the sample space. So notice our new notation, little n means number of outcomes, in this case, the sample space. All right, so there you go. So this is one way to calculate our probability of 2 events. Something else that we could see is if we separate our fractions right here, number of E over number of S plus number F over number of outcomes in S. Let's see, I'm going to have to write it very small. So we can separate our fraction like this. And then when we do that, we actually see that those are just probabilities. That's the definition of a probability. So now we have our addition rule for disjoint events. So let's write it like this. So probability of E or F. All right, so remember we did all that work to get this, but that is just simply the probability of E plus the probability of F by definition. So this is our rule when we have disjoint events. So the addition rule for disjoint events is this right here. Okay, and then again, what that or means, the outcome can be in one or the other, E or F. It does not have to be in both. And we're going to find that this just lets our probabilities get bigger. Our events get bigger. So that's why we're adding. And I like to write this little rule at the top. The addition rule is for when we see the word or. When we see this keyword or, the operation we have to use is addition. All right, so let's look at some simple examples. So here we're asked, what is the probability a random selected housing unit has 1 or 2 or 3 rooms? All right, I always like to write down what the problem's asking. So it's the probability of 1 or 2 or 3 rooms. So we get to do our addition rule twice. So notice that all of the rooms in this housing units, right, there's 1, 2, and 3. They're disjoint. There's no way a housing unit can have both 1 room and 2 rooms at the same time. So according to our addition rule, or means plus. So we're going to look at the probability of 1 room plus the probability of 2 rooms plus the probability of 3 rooms. All right, and then we're given all those probabilities. So essentially we have to add up those numbers. I'll write it in a different color. So we're looking at 0.1010, plus 0.032 plus 0.093. All right, and if we add all of those up, we get 0.135. All right, so a very straightforward, very simple example of the addition rule. So let's consider events that are not disjoint. All right, so let's say my event E, I'm going to define it. We're still rolling a die. So let's say I'm going to allow it to have a 2, 3, 5 in event E. And we'll say event F. We roll our die and we can get a 2, 4, 6. Do you see the outcome that is in common? The 2. So these events are not disjoint. They have that outcome in common. Okay, so now we would want to know what's the probability of E or F occurring. So probability of E or F. So let's draw a picture. Let's draw a Venn diagram. So just as before, let's start with a rectangle. This is our sample space. And we have 2 events, and there's an outcome in common. So our circles are going to overlap. And where they're going to overlap is that 2. All right, so for instance, event F has 2, 4, 6. And event E has 2, 3, and 5. Okay, so we can look at this. Again, this is a counting game. How many, oh, let's finish actually this drawing. So I'm going to put 1 on the outside. 1 is on the outside. Okay, so it's a counting game. Probability of E or F now, we can count how many outcomes are in both events. 1, 2, 3, 4, 5. So the probability of E or F is going to be 5 in both events over total outcomes, so 6. All right, but now look at this. If we were to use our old formula from before, here I'll write it in a different color because it's not going to be correct. So probability of E or F. So according to our last formula, for disjoint events, events that did not have a common outcome, we could do something like this. Probability of E plus probability of F. All right, so probability of E, well, there's 3 outcomes in E out of 6. And probability of F, there's 3 outcomes in F over 6. And now look at this. If we add up those fractions, we get 1. So that means that's a sure thing. So we're always going to get, when we roll a die, a 2, 3, 4, 5, or 6. That's false, because we can also get a 1. So it's not a sure thing. It should be 5 over 6. It shouldn't be 100%. What happened here is when we were doing all of our counting, we counted this 2 twice. We counted it once in the first 3 over 6, and then we counted it again for the second 3 over 6. So what we have to do is we actually have to subtract the overlap. And that's what we call that 2. The 2 is the overlap, the common outcome. So here's the general addition rule. This is for any 2 events. Not mutually exclusive events, not disjoint events. So for any 2 events, if we're looking at the probability of E or F, we're going to start off as before, probability of E plus the probability of F, but we don't want to count the overlap twice, so we have to subtract it once. So we're going to call the overlap, well, that were all the outcomes that were in both E and F. And that's our formula. So again, let me just write out what I just said. And remember, the outcome is in both E and F. Okay. So let's look at an application of this, and we're going to use the general addition rule. So now, let's say 2 dice are thrown. All right, and we're going to define the following. We're going to let E, that event, be the first die is a 2, and event F is going to be the sum of the die is less than or equal to find. And we want to find probability of E or F. All right, so this can definitely be solved by counting, but we're going to use the general addition rule because they asked us to. So the probability of E or F, according to our rule, is going to be the probability of E plus the probability of F minus the probability of E and F. Okay, so let's see how we're going to do this. So first of all, what's the size of our sample space? I'm just going to use multiplication. We have 1, 2, 3, 4, 5, 6 columns. 1, 2, 3, 4, 5, 6 rows. 6 times 6 is 36. So just a little note, the size of our sample space is 36. All right, so now we're going to figure out how much are in event E. So event E is the first die is a 2. So if you notice how this is organized, the second row, all of the second row has the first die of 2. So everything I'm highlighting is event E. So how many pairs of die, how many outcomes are in that event? 1, 2, 3, 4, 5, 6. So event E, probability of event E occurring is 6 outcomes out of 36 total in the sample space. All right, now let's consider event F. The sum of the dice is less than or equal to 5. Okay, so let's start at the top. The top row, the first die is a 1, so let's add them up. 1 plus 1 is 2, so that's part of event F. 1 plus 2 is 3, that one's coming. 1 plus 3 is 4. 1 plus 3 is 5. And then 1 plus 5 is 6, that's too big. So let's go down to the next row. 2 plus 1 is 3, that's coming. That sum is 4. 2 plus 3 is 5. All right, and then 2 plus 4 is 6, so we're done with that. Next row, first die is a 3. 3 plus 1 is 4. 3 plus 2 is 5. And then 3 plus 3 is 6, that's too big. And then finally the fourth row, where the first die is a 4. 4 plus 1 is 5. So there you go. So let's count up everything we have there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 outcomes in event F out of 36 total outcomes. All right, and now let's talk about the overlap, because we have to subtract the pair of dice that's in E and F. And that's the one where the highlighter became green. Yellow and blue make green. So it's the second row and then all the dice that added up to 5 in that row. And there was 3 combos that added up to 5, less than or equal to 5, and whose first die was a 2. Okay, so there's our solution. All our numerators are the same. 6 plus 10 is 16, minus 3 is 13. So your solution is 13 out of 36. Also note, we could have just done this by counting. We see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 outcomes in event E or F. All right, let's look at another example now. This one has to do with the deck of cards. So if you're not familiar with the deck of cards, there is a chart in your textbook that shows all 4 suits with all 13 cards in them. And example 3 says 1 card is randomly selected from a standard deck of 52 cards. And we want to compute the probability of randomly selecting a heart or club from a deck of cards. So first great step is always to write out what we're trying to find. Probability that we get a heart or a club from our deck of cards. And these are suits, and there's 13 of each suit. So 13 out of 52. And these are mutually exclusive, so we can just look at the probability of hearts plus the probability of getting a club, and there's no overlap. So that's how we set up that problem. Same denominator, so we're looking at 26 over 52, which is half. All right, and again, remember when we see this word or means addition, or means addition. All right, the next one's a little bit different. We want to compute the probability of randomly selecting an ace. So I'll write A for ace, or a heart. So again, or means plus, but now there's an overlap. There's an ace of hearts. So our rule starts off the same as before, but we don't want to count the common outcome twice. So we're going to subtract it once. We're going to subtract the probability of being an ace of hearts. Okay, so there's 4 aces in a deck, so 4 out of 52. There's 13 hearts in a deck, so 13 out of 52. And there's 1 ace of hearts. So that's how we're setting up our probabilities. Same denominators. 4 plus 13 is 17, minus 1 is 16. So we can just write it as 16 over 52. If you wanted to reduce it, you can. And that was going to be 4 over 13. So there you go. All right, so the next part of this section is called the complement. So we're going to look at the complement of an event now. Let's go back to rolling a die. So remember, the sample space is the same as it was before. 1, 2, 3, 4, 5, 6. Okay? And let's define our event E to be rolling an even number. So we can actually write that out, roll an even number. Even numbers are divisible by 2, so 2, 4, 6. Okay, so let's set up our Venn diagram. Here's our sample space. Here's our event, E, and 2, 4, 6 are in the event. So what's in the sample space? What's left over? 1, 3, 5. And that 1, 3, 5, those are outcomes outside of E. We call that the complement of E. So the complement of E which we notate as e to the c, e to the complement, the c is an exponent. It's whatever is outside of e. So 1, 3, and 5. So it's outcomes outside of the event. Outcomes outside of the event. I'll write that down. Okay, and then this is why complements are important for us. E, the event E plus the complement makes up the whole sample space, right? And so if we were to look at these probabilities, probability of E plus probability of its complement, it's also going to be equal to the probability of getting something in the sample space. Well, what is the probability of getting something in the sample space? It's 1. So this is our rule. This is why this is important. The probability of an event, let's do a little bit of algebraic manipulation. We're just going to subtract the probability of the complement from both sides, and we're going to get 1 minus the probability of its complement. All right, so let's see this in action. It's more intuitive than the formula. For instance, according to this association, 31.6% of Americans own a dog. What is the probability that a randomly selected household does not own a dog? Well, it's the opposite, right? So I think very intuitively, we would know that it has to be the rest of the population. So you would take 100 minus 31.6, and we would say that 68.4% do not own a dog. Relating it back to what we just did with our formulas, we would call event E owning a dog, and the complement is kind of like the opposite. The complement would be not owning a dog, the opposite. Okay, so we know the probability of owning a dog is 0.316. So the probability of not owning a dog, here's an alternative to the formula, just switch them around, would be 1 minus 0.316, which is 0.684. What we got intuitively before, but we again are just relating it back to our formula. Okay, so let's see how the complement can make our life easier. Let's look at this next example. This data represents the travel time to work for residents of Hartford County. Compute the probability that a randomly selected resident will have a commute less than 90 minutes. All right, look at these travel times. Look at these classes. Less than 90 minutes is everything but that last class. Okay? So rather than adding up all of that stuff, we can use the complement. All right, so this is what we're going to do. So we want, the event is the residents that have a commute time less than 90 minutes. I'm just going to write it like that. So what's left over? What would the complement be? Commute times that are greater than 90 or more minutes. All right, so according to our rule, the probability of E, what we're trying to find, resident has a commute time less than 90 minutes, it's going to be 1 minus the probability of the complement. So rather than adding up all that highlighted in red, we can just look at the probability of the complement. So 4,895 over the total amount of residents. I'll tell you what that is. There's 393,186 residents. So that's the total frequencies. Okay, and we can just put that in our calculator, and we should get about 0.9876. All right, so again, rather than adding up all that highlighted in red, we could use the complement to make our life a little bit easier. Okay, let's look at our final example. We have a table, right? We have two variables going on. This one, the row variable is uses social media, does not use social media, and the column variable are the ages. So they asked Americans whether they use social media, and they organized it by age. So let's see what we're looking at. So if an adult American is randomly selected, what is the probability he or she uses social media? Okay, so they don't ask anything about age, so they just want to know if they use social media. So we saw this in section 4.4, where they look at the totals, the row totals and the column totals. So for this one, we would look at the column total. I'm just going to highlight in red. So all this in red represents people that use social media. And so we're looking at 338. They already did the totals for us. And now remember, this is the total of the totals is how many people are in the survey. So we're looking at this. So the probability, we can put that in our calculator, is 0.638. Okay, let's compare that to the next one. If an adult American is randomly selected, what is the probability he or she is 35 to 44-year-old social media user? All right, well, that's very specific, right? A 35 to 44-year-old social media user. Well, that's just this one cell. So we're kind of looking at the overlap, the probability that they're 35 to 44 years old and a social media user. Well, that's 89 over the total in the sample. Okay, and then part C is relating it back to what we were just looking at. If an adult American is randomly selected, what's the probability he or she is 35 to 44 years old or uses social media? Let's write that out. And we see that word or. What's that operation? Addition. So we can break that down according to our rule like this. I'm going to abbreviate social media by just SM. Is there an overlap? Yes, that was what part B was. Part B was 35 to 44 years old and social media user. All right, so we have all of these components right now. So let's see, the probability they were 35 to 44 years old, that's this column. So we have to look at that column total, 125 out of the total, 530. Probability they're social media user, we did that in part A. And probability it's a 35 to 44-year-old social media user, and they use social media, that's 89 people out of 530. All right, so we can put that in our calculator if we would like, and we get 0.706.